Good morning, guys. Today I'll be talking about color centers on hydrogenated titanium dioxide facets and how that has allowed it to unlock fluorescence detecting in this kind of sample. So titanium dioxide is a compound that is not normally found. It has to be made through a process called sulfate process. Sulfate process has three main steps. The first one is called dissolve ore. Pretty much in this process, they take iron titanium oxide, as seen in this equation here, and it dissolves in sulfuric acid to form a mixture of sulfates. Before it can be extracted, the iron ions have to be removed so it allows it to get a pure white color. And there, the recycled iron sources can then be converted to iron 3 ions that can be present in iron 2. From there, that aqueous solution is clear and then it's poured off before it's even concentrated. From here, after the concentration, the formation of hydrogenated titanium dioxide happens, and this is usually the result of hydrolysis of titanium sulfite to give insoluble hydrogenated dioxide. From here, you go on to step 3, which is that anhydrous titanium dioxide. In this step, heat is introduced in order to evaporate and decompose any sulfuric acid that still remains solid. This, as a result, will allow for the formation of titanium dioxide solids in the sample. One of the most fascinating things about titanium dioxide is its chemical stability and its photocatalyst ability. So what that means is that it's very good at dispersing light. So if you shine light at it, it's very good at reflecting. The problem with that is that it's a semiconductor and it lacks fluorescence. So there's two ways to make up for that. So scientists can do a process called fluorophores. The only problem with that is that it affects the stability of titanium oxide by changing its shape, size, and or surface. So there's also something called doping. Doping, however, also causes a problem because it diversifies the dopant locations and the confinement of the excitation energy in the molecules. So the only option scientists have found and a method of work is something called hydrogenation from titanium dioxide. It's a dopamine-free approach to engineer the electric constructor to provide titanium dioxide with strong and streak fluorescence by introducing self-structural modification of oxygen, vaccine TiO, and titanium 3 plus and sulfate surface disordering. This will give fluorescence by exciting that titanium's 3D orbital. So the whole purpose of this experiment was to develop a dopamine-free titanium dioxide with the streak fluorescence grounds on the understanding of photoluminescence of hydrogenated titanium dioxide facets. The facets that were ran were the 001, 100, 101, and 201 facets. As you can see in this equation, when they were ran, this is what they reflect. A dark gray, blue, gray, and a pale gray, respectively. And the way it works, the simple fluorescence is illustrated here, how the color centers and the excitation of energy produces a fluorescence. So what they found, one of the results they found among many, is that VO and the titanium sites have an influence in electron localizations due to the VO formation that can localize VO and titanium sites to demonstrate different colors of electron-pragmatic resonance by the signals of VO that is given. For example, the G is equal to 2.002 and titanium is at 1.989. What this revealed is that they're localized on the surface of VO sites. Oxygen was then introduced to understand how VO diffusion and electron distribution works. And it showed that VO resides on the substrate and prevents reactions with the surface of oxygen that is then calculated for the minimum energy pathways. So here are the results they got from those experiments. Another interesting result they got is how the VO contributes to the mid-gap state of the facet-dependent to diversify titanium 3D orbitals redistribution. The specific field of titanium oxide, octathone, shows degenerate of titanium 3D pi, titanium D orbitals. The titanium D orbitals show degrees of dealkalization energy. Broadening, as you can see in this illustration right here, is how they look once they got ran. But the main finding they found, and what can be used for further research on how to use, for instance, imaging to use this, is because the hydrogenation of titanium oxide by the VO and the titanium 3 plus has a highly facet-dependent and hydrogenation of 201. And it's capable of showing fluorescence imaging. Not all hydrogenations, like as you saw, there was multiple ones like 01, 100. They were not as capable of reflecting that good image as this one was. And that is the result of VO formation and diffusion, electron localization on the VO and titanium 3 plus. The redistribution of the electronic states and the PO emissions from the color centers. And this is just a general image of what they really found. Okay, so from this, I use the general concepts of how electrons are being moved around, the wavelengths, to do three main problems. My first problem, it's a one problem, but it has three main components. So the problem reads as follows. Titanium dioxide was ran through the photoelement's emission, and the mapping shows excitation at 256 nanometers from the photon hitting an electron. These are the potential information that can be used in order to solve these equations, these problems. And the diagram on option B will be used in order to really do part A of the problem. Because without this, it's honestly very hard to do just like that. So the first problem talks about electron configurations of titanium and oxygen and show the term symbols at the ground state from those informations along with that image I showed you. You have to obtain that in order to see an approximation of how titanium oxide will look as far as the molecular orbitals go. So titanium has electrical configuration of argon 3D 2 4s2. 3D, as you guys know, since it has a little slight energy difference, you can flip it. Instead of having 4s squared, 3D squared, it can be flipped around. And this configuration allows for the 3f2. Oxygen, on the other hand, will give a helium 2s squared 2p4, and this gives the term symbol of 3p2. In order to make the molecular orbital, this diagram was used because titanium is a transitional metal. It's not a diatomic interaction, so it's a little bit different. So from this structure, it gives you this. It's pretty much you can come out with this structure right here, where these will show the states and abbreviations. This will show the orbital it's in. From that, next, the problem asks to calculate the work required to eject the electrons at 2 eV to find the threshold frequency and kinetic energy. So what we know is that kinetic energy, to find the threshold, the kinetic energy of photoelectrons can be given as K is equal to hc over lambda plus work. So we solve for work, it gives us K minus hc over lambda. Plug in our information. We have 2 volts. Because it's measured in joules, you have to do a conversion. And we use Planck's constant, speed of light, and our wavelengths. That should give us a work of 3.19 e to the negative 19 joules. Next step will be to find kinetic energy. So kinetic energy is a byproduct of the energy of the photon minus the energy required. So to find, we just consider the work function. So the work function is equal to HVO. VO can be found as the EO sigma over H hat. The EO will be given as the work function, which is the 3.19 negative 19 that we found from the last problem, over Planck's constant, and this would give us 4.62 E14 hertz, the frequency needed. From here, now we can solve for kinetic energy. So we know that electron photon can be given as HV and can be further reduced into hc over lambda minus the work function. Plug in our numbers that we got from the previous results. So 6.62, Planck constant, speed of light, wavelength, minus work function gives us 7.95 e to the negative 19 joules. From all the information that's been calculated in the previous question, we want to find Broglie's wavelength. On top of that, then we want to calculate the electron diffraction of a 1 nanometer slit if the detector is 1 millimeter behind. Just because we're using photoluminescence imaging, so I figure this problem would be perfect for that. So what we see is that Broglie wavelength is h over p, which can then be rewritten as h over mv, where b is frequency and can be substituted as mass times. And if you manipulate the kinetic energy of, 1/2 mv squared, will give us 2 kinetic energy over m. Using simple algebra, we can simplify it as h over the square root of 2k em. Plug in our numbers. Don't forget the conversion. That should give us 5.5 e to the negative 10, or 5.5 astronomical units. To find the electron diffraction, we have to find the angular width of the first maxima. This can be given, as you can see this as a triangle. So that's why to find that, it gives the formula of d sine of theta is equal to sigma m. Solve for the sine of theta, and we get 33.4. To find the width, we got to find the tangent. So tangent can be given as the width over 2 over the length. So when we solve for width, we get 2 tan theta times the length. So it'll be 2 theta 33.4 times 1.0 e to the negative 6. That gives us a width of 1.31 e to the negative 6 meters. Thank you. Hope you guys like it.